Hi, this is Professor Fernandez. We're going to work on Class Notes B in Lesson 12. So the first question here for this example is, what is CSA? So let's scroll up a little bit so I can remind you what that notation means and what the concept is about. So CSA is up here in definition 12.1.1, and that refers to the column space of A. So what is this? It is the set of linear combinations of the columns of the matrix A. All right. So, some little backstory for this. I'm going to scroll up even a little further to remind you of why and how this concept came about. This was the calculations from the previous video, and here's where the concept comes about, right? In the previous class notes, we show that when you multiply a matrix times a vector, what you get is actually a linear combination of the columns of the matrix. Okay, so that's when you multiply a matrix A times a specific vector with components x1 through xn. So the idea of a column space is, what if I look at all possible combinations, linear combinations of the columns of A? That's exactly what the column space is. Okay, so now that we reviewed that concept, let's go back down to the example and then calculate for this example the column space, and then we'll do number 2 later. So what is the column space of A? Linear combination of the columns. So I'm going to write it out using the columns of this matrix, which is 1, 0, 0. Second column is 2, 1, 0. Third column is 4, 2, 0. Such that all of the x's here are real numbers. Okay, so it's pretty much that simple. That is the column space of A. For some applications, it might be to your benefit to check if the columns of A are linearly independent or not. Because although this is the expression for the column space of A, if there are vectors that are linearly dependent, then you can just remove them and get a simpler expression for the column space. That might be useful sometimes, for this second question, for example, it might be useful to help you find solutions to linear systems that involve the matrix A a little faster. I'll just mention here, for example, I did this deliberately. If you look at this matrix and you look at its second and third columns, second column and third column, you'll notice that the third column, 4, 2, 0, is literally twice the second column, 2, 1, 0, right? 4, 2. So, these three vectors down here are linearly dependent because there is some relationship between them. But I'm not going to, worry about reducing the column space expression we've written down to one that doesn't involve one of these linearly independent vectors. Long story short, what you would do to do that is you could effectively just cross out one of these vectors, the one that is the dependent one, and then reduce the column space to just a linear combination of the independent ones. Because again, you could get this third column by combining, in particular in this case, in this example, just the second vector, just scaling it by 2. But anyway, I'm going to leave the column space as is. That is not the most simplified presentation of the column space, but it is the column space nonetheless. So number 2, write out a set of equations that answers the question, for what b does ax equals b have a solution? Okay, so this is a different type of question which is connected with one of the concepts that's being introduced in this lesson. We are trying to reframe questions about solving ax equals b, which have been traditionally in the form given b and given a, find x. Now we're trying to reframe them to move toward a slightly more general understanding of this problem. Given a and not given b, for what b does ax equals b have a solution? Okay, and we understand now that the answer has to do with the column space of A. So let me just scroll up a little bit to remind you where that pops up. And that's this theorem up here, theorem 12.1.2. So the system of linear equations ax equals b has a solution if and only if b is in the column space of A. All right, so that should make a lot of sense because, again, as I say up here, ax equals b by the theorem prior to this one is a linear combination of the columns of A. So, this linear equation is the same as this one. And the only way this is going to have a solution is if indeed b equals a linear combination of the columns. And the column space is the set of all linear combinations of the columns of A. So that's basically one, verbal proof of one direction of this theorem. Okay, so now that we know that, we're going to scroll back down and continue working on this example. So it says, write out a set of equations that answers the question for what b does ax equals b have a solution. Okay, so I'm going to just write a little bit of what we just talked about. For ax equals b to have a solution, we require that b is in the column space of A. Okay. We have just calculated the column space of A up here. So this implies that b must be equal to some linear combination that looks like this for some xi in R. Okay, and then if I just think of b as a vector with components b1, b2, b3, and then I write out the right-hand side here. I'm just going to do the multiplication. This is x1 plus 2x2 plus 4x3. And then this is 0x1 plus x2 plus 2x3. So x2 plus 2x3. 0x1 plus 0x2 plus 0x3. So this is 0. All right. So this is what the relationship must be between the components of B and the unknown coefficients x1, x2, and x3 in this linear combination up here. Right? It must be true that x1 plus 2x2 plus 4x3 is b1, x2 plus 2x3 is b2, and that b3 is 0. You can already see how this helps, because if I asked, for example, a follow-up question, so anyway, this is our answer to number 2. For what b does ax equals b have a solution? In this case, this is the answer. B has to be expressible in this form. So to give you an example, what if I asked you, does this system have a solution for b equals 7, 2, and 10? Okay, the answer would be no, because this condition down here would be violated, right? This condition says that the third component of the vector b must be equal to 0, and this third component is 10. So you can already tell it is not going to have a solution. So that's just one way that you can use what we're doing to help you answer questions that we haven't really been able to ponder before. For what's b does ax equals b have a solution?